In section 1.4, we'll be creating functional models. Basically, the idea of this is to take a word problem scenario situation and create the aspects of that problem to turn it into a function. And then we can do all sorts of things with functions. In general, we like to find the largest value of the function, the smallest value of the function, whatever it is, right? But we are creating the functions, and that's our focus today. Example 1 says, a farmer wants to build a rectangular pen for horses. He has 600 feet of fencing to use. Find the dimensions of the largest possible pen and what is the largest possible area. So a couple of things I want to do first is sort of break this down and note the important words here. First off, we know it's going to be a rectangular pen, so we need to create a rectangle. We have 600 feet of fencing to use. And the question there is, how does that translate into something that is geometric? Well, 600 feet of fencing is what you would use around the pen, so that must be the perimeter. And then it says, find the dimensions of the largest possible pen. Well, what do we mean by largest possible pen? Well, we're talking about area, right? We're talking about the amount of space that the pen encloses. So we want the largest possible area, and then it says, what is the largest possible area? So that's how we get started. We know we need a rectangle, we have information about the perimeter, and we want information about the area. So usually, if it's a geometric type problem, I like to draw the picture first. And just any old rectangle will do. And then I'm going to label the sides. This is going to be X and X, and then this can be Y and Y. You can use L and W if you want, but I like using the X's. It's more familiar to us. And then I'm going to write out the information about my perimeter. Now, you don't necessarily need to know the perimeter formula for a rectangle. If you do, that's fine. It's great. But here you just add everything up. You got 2 X's and you got 2 Y's. So it's 2X plus 2Y, and that's equal to 600. All right, let's leave that alone for a second. Then I'm going to come over here and I'm going to talk about the area. And the area of a rectangle is length times width. So that's X times Y. Now the problem here is I have 2 different variables. I have an X and a Y. And I really want to reduce this down to 1 variable so that I can use all the stuff I know about functions right now. So the key here is to solve this original equation. And I'm going to solve it for Y so that all that remains are the X's. And so first I'm going to move the 2X to the right side. And then I'm going to divide everything by 2. So it's going to be 300 minus X. Now I'm going to substitute into the area equation. And because I solved for Y, and I'm going to drop it right in here for this Y right here, so it's 300 minus X. Now you'll notice that all I have are X's. So now this isn't just A, but this is A of X. It's now a function. A is a function of X. So what we've created is the functional model for my rectangle. What this allows me to do is I can just pick any value of X and say, okay, that one side of the rectangle is going to be whatever my X value is. I plug it into this function, and it tells me what the area is. I don't even have to worry about the Y. We already know what the area would be just based on this function. Now we want to use this to find the largest possible area. So I'm going to multiply this out. And if it helps, I'm going to rewrite it in standard form here. And then we think, okay, well, how could we find the largest area from this? Well, we're going to learn some new techniques in future sections. But for today, what we want to know is that it is a quadratic. And to find the maximum of a quadratic, we use that vertex formula from a few sections ago. So that's going to be x is equal to negative b over 2a. The b is positive 300. The a is negative 1, because it was negative x squared. And that is going to be 150. So that is the x value that creates the maximum area of a rectangle whose perimeter is 600 feet. Now I need to find the other aspects. So what are the dimensions? So x is one of the dimensions. So we know that. Plug that in. That's 150. And to find the y, I'm just going to use this equation from before. So y is equal to 300 minus 150. And that's also 150. So I'm going to go ahead and put labels on these units. This is going to be 150 feet. So the dimensions are 150 feet by 150 feet. And yes, that is a square, and all squares are rectangles. So that's fine. It just turns out that the square is the rectangle that produces the maximum area. That makes sense. And then the final part of this is, what is the largest area? So I'm going to plug in 150 into the area formula to find the area of this square rectangle, 150, and that's going to be 22,500. Of course, you could have just multiplied those out, 150 times 150, but I did want to demonstrate how you can take the number and just plug it back into the function that it came from to get that value for the function. All right, let's take a look at example number 2. Now suppose that the farmer decides to build the pen against the side of a barn. Thus, only 3 sides of the pen require fencing. What are the dimensions of the largest pen, and what is the largest pen? So we have sort of the same situation, it's just slightly different. So we have the barn here. And then the pen is going to be coming out of this right here like that. It's a little rectangle. I've drawn it sort of skewed because it's, perspective and stuff, but it's a rectangle. Now the key here is that you only have 3 sides of fencing. And so when we go to write our perimeter formula, there are still 2 x's, but there's only 1 y. So it's 2x plus y is equal to 600. All right, let's hang on to that. Let's do the area formula again. It's x times y. And so I see again I have 2 different variables, x and y. I just need the x. So I'm going to solve this for y. And then I'm going to drop it in. It creates another function. So it's x times 600 minus 2x, which is 600x minus 200x squared. And again, we can rewrite this in standard order here. And we want to find the max. So the max occurs when x is equal to negative b over 2a, which is going to be negative 600 over 2 times negative 2. Well, that's 150 again. That's no problem. And then what would the y be? Be 600 minus 2 times 150. And that's 600 minus 300, which is 300. So the dimensions now are going to be 150 feet by 300 feet. And then a of 150. Now you may say, well, why did I choose 150 and not the 300 to plug into the a? Well, remember what a is. A is a function of x, and the x is 150. The y is 300, but my function a is not a function of y. It's a function of x. So this is negative 2 times 150 squared plus 600 times 150, and that is equal to 45,000 square feet. And there you go. Example number 3. An open-top rectangular box must be designed to hold 6,000 cubic feet. The base must be 12 feet wide to fit into the allotted space in the warehouse. The material for the lateral sides cost $4 per square foot, and the material for the base costs $10 per square foot. Find the dimensions of the box that minimize the total cost of building the box. What is the minimum cost? So again, we have sort of a geometric question. I need an open top rectangular box. Open top means it only has 5 sides. There's no top. The other sides, the bottom, the 4 sides around the box, those are fine. It holds 6,000 cubic feet. So cubic feet tells me that this is volume. That's also, what does a box hold? It holds volume. So we know that. The base must be 12 feet wide. Okay. The lateral sides cost $4 per square foot. The base cost $10 per square foot. Find the dimensions of the box that minimize the total cost of building the box, and what is that minimum cost? So we're looking for a cost function. So first, let's draw a little picture. I'll draw my box here. Something like that, so that you can just sort of visualize that. And let's use the volume part first. So what is the volume? Oh, I need to label my box. Hang on, let's label my box. So I'm just going to call this 12. I'm going to call this X, and I'm going to call the height H. Now let's do my volume. So my volume is going to be length times width times height. So it's going to be 12 times X times H. And I know that that is equal to 6,000 cubic feet. All right, let's hold on to that for a second. Next, we need the cost function. So C is equal to, and now I'm just going to add up the cost of all the sides of the material for the box. So the first one we have here is the lateral sides. The lateral sides are the ones that rise up. So let me mark this lateral side here, and there are 2 of these type right back here. So the area of this lateral side is X times H, because it's a rectangle with length X and width H. There are 2 of them. I'm going to multiply that by 2. And the cost for that lateral side is $4 per square foot. So this is the total area of those types of lateral sides, and that is the cost per area, right? Cost per square foot. All right, next, I'm going to look at this side here, which has an accompanying side over here. So this is going to be, the area of that is 12H. There are 2 of those again. And the cost for those sides is $4 per square foot as well. Again, that comes from area, and then the cost per area. And then lastly, we have the base down here. I'm gonna draw in a little more base so you can see it. I guess it goes all the way here. So the base is down here like that. And that base, well, there's only one of those. The area of that base is 12x, because it's a 12 by X down here on the bottom. But the base costs $10 per square foot, probably because it's made of a thicker material to hold the contents of the box. And so once again, this was area and cost per area. All right. So now we're going. All right, so now let's simplify this as much as we can so far. So 4 and 2 is 8, so it's 8xh plus 2 times 12 times 4 is 96h, and then 12 and 10 is 120x. So we have the same problem as before. We have a function, but it has two different variables. We have an x and an h. So I'm going to go back to my volume function, and I'm going to solve this for h. So h is equal to 6,000 divided by 12x, and 6,000 divided by 12 is 500. So this is 500 over x. And I'm going to substitute that into my cost function. That makes it cost of x, c of x. And I'll replace the h's with 500 over x. So it's 8x, 500 over x, plus 96 times 500 over x, plus 120x. So now I'm going to simplify this. 8 times 500 is 4,000. And then the x's cancel. 96 times 500 is 48,000. There's still an x in the bottom there. And then 120x. All right. So that is our cost function. And we're still looking for the minimum value of the cost function. Well, this is a rational function. It's not a quadratic, so we can't use the trick that we did before. And part of this course is learning how to solve problems like this. But we don't know how to do it using calculus yet. But we will. That comes in chapter 3. So what we're going to do instead for now is we're just going to use the graphing calculator. And so I'm going to go ahead and graph this on the graphing calculator. And we're going to make a window here. And the window is going to go from -1 to 50. And from -2,000 to 20,000. Now, you get better at making windows the more you practice with some of these things. But the idea is to look for function values and try to find the x's where, you know, what you're looking for is going to happen. So we know it's going to happen at a fairly small number, between 0 and 50. And then try to make the y values coordinate with the values of the function itself. Now, when I graph this, then what I can do is I can go to Second, Calc, and we're looking for the minimum. So go down to minimum and press enter. And then drive the cursor to well before the minimum and press enter. And then drive the cursor through the minimum until you see it rising again. Press enter again. And for the guess, you can just press enter. It'll usually find it. And then the calculator will compute the minimum, and you can see that the x is equal to 20. So the one dimension of my box is 20 feet. I need to find the height of the box. Well, we have a formula for h. H is 500 divided by x, and the x that I want to use now is 20. So that's going to be 25 feet. So the dimensions that minimize the cost of this box is 20 feet by 12 feet by 25 feet. And finally, we need to find the minimum cost. So I'm going to use C of, and I'm going to plug this into the function. And the x value that we found and we're working with was 20. And so we plug that in, and we get 4,000 plus 48,000 divided by 20 plus 120 times 20, and that's equal to $8,800. And also, you could have seen the y value when we found the minimum should have been 8,800 as well. Finally, we want to talk about market forces and market equilibrium. So here's the graph, and this is your typical supply curve and demand curve. And the question is, what's happening at different points along this curve? Well, let's say that the price of an item is right here. Well, that's a problem for the market, right? Let me just draw this line over here. If the price is whatever this is right here, then that means that the demand is very low, because the demand is down here, right? This is the demand, but the supply is quite large. And so that means the producers are producing more of the item than what the consumers are willing to buy. And that leads to a surplus. All right. So that's a problem. Let's clear this out. Let's suppose that the price was somewhere else. Let's suppose that instead the price were to be down here. Well, now we have a demand that is really high, but for that price, the producers are only willing to supply the market with so many items. And so now we have a shortage because people want more of the item than what the producers are willing to produce. So this all has to sort of work itself out until you get to the point where the price for both the demand and the supply are the same. So the price is here, and that is the same demand. And that is called market equilibrium. So this special point is denoted by PE, and then the quantity that's demanded is XE. And this is market equilibrium. In other words, the consumers are demanding the same amount of items as the producers are willing to make, because the price is just right for both of them. And everything is fine. So that's market equilibrium right there, this point here and here. And then if we're in this area up here, we have a surplus, as talked about before. And if we're in this area down here, we have a shortage. And it just depends on which one is larger in terms of quantity, depending on where the prices are and things like that. Example number 4. Market research for 2-liter sodas reveals that when X thousands of units are manufactured and sold at a local grocery store on a monthly basis, the supply and demand functions are S of X is equal to 0.8 plus 0.06X, and D of X is equal to 3 minus 0.10X. Find the number of 2-liter sodas that should be produced and sold to achieve market equilibrium. And then what is the price per soda at equilibrium, and when is there a surplus, and when is there a shortage? All right, so if we want market equilibrium, we just set S equal to D. So we set these two equations equal to each other. And we solve for X. So I'm going to move the negative 0.10 to the left side. That gives me 16x. Then I'm going to move the 0.8 over, and that's going to give me 2.2. And so x is equal to 13.75. Now here's the kicker, right? X was in thousands of units. So it's okay to have a decimal here. And the actual number of 2-liter bottles that are going to be sold, so number of 2-liter sodas is actually 13,750. Because we multiply that by thousands in order to get the actual quantity. And then to determine what the equilibrium price is, we plug it in. Now, at equilibrium, the supply and the demand produce the same price. So I can choose either one. I will choose the D. I will choose the demand. And you have to plug in the X value, not the actual quantity, because of the way that the functions are set up. And that is $1.62.5. So it's about $1.63. And we'll just leave it like that. That's fine. So that's the equilibrium price equilibrium for 2-liter sodas. That's actually about right too, I think. Maybe it's a little high. That's okay. I know personally I like to buy Dr. Peppers when they're on sale, but that's okay. All right, so here's X, and then here's the price. And now we're going to graph these. So I'm going to graph the supply curve. The supply curve looks something like this. And that's just a linear equation. It's all relative here. And then the demand curve, we know that that starts at 3, and it's going to go down. So it's going to be something like this here. It's a straight line. And then this point right here is price equilibrium, which was this. And then we have market equilibrium, which was this. And the actual number was that. Now, where do we have a shortage and where do we have a surplus? We have a surplus up here. So that means the producers are producing too much for what the demand is. And then down here we have a shortage, which means the demand is too great and can't be filled by the producers. All right, now let's mark these numbers here. Mark this number here. This was $1.625, and this was, go ahead and mark it as 13,750. Right there. All right. Thanks for watching.